Okay, so um, have you ever wondered how computers are learning to actually see the world? Like not just processing an image, but actually understanding what's in it.
It's pretty amazing, right? We're talking about things like medical diagnoses from x-rays or even self-driving cars navigating a busy street.
And a lot of it comes down to this really cool technology. It's called UNet. Basically, it's all about image segmentation.
Right, so instead of just seeing a jumble of pixels, imagine giving a computer an image and it can pinpoint and outline every single object, every boundary, just like we do. That's the power of UNet.
It's mind-blowing. But here's the thing. While it's been incredibly successful, figuring out why UNet works so well, like what's going on under the hood, has always been a bit of a mystery.
Yeah, it's like this amazing magic trick, but we don't know the secret behind it.
Exactly. And that's where this research paper comes in. It's called A Mathematical Explanation of UNet.
And it's trying to demystify UNet to show us that it's not just some, happy accident, but a system that's actually built on really elegant mathematical principles.
Okay, so let's unpack this a bit. The paper, it frames UNet as a control problem. Now, I know that might sound a bit intimidating, but stay with me.
Sure. So think of it like steering a ship, right? You have this goal to reach a specific destination, but the wind, the currents, they're constantly pushing you off course. To stay on track, you need to constantly adjust your steering, always thinking about your current position and where you want to go.
So it's all about making those small adjustments, those course corrections to actually reach your final destination.
Exactly. Now imagine that ship is actually our image segmentation process, and the destination is the accurately segmented image.
Okay, I think I'm starting to see where you're going with this.
The control problem lies in figuring out the best set of instructions, those precise adjustments to guide that process towards our desired outcome.
So UNet is basically figuring out how to steer the image processing to achieve that perfect segmentation.
You got it. And the interesting thing is, those steering instructions in this case, they're actually mathematical equations. The paper, it dives into these equations, showing how they act like the ship's rudder, basically guiding the entire process.
Now, this is where I always imagine things got super complicated. Like we're talking, complex equations, algorithms.
Yeah, it does get pretty deep. But the core idea, it's surprisingly elegant. One of the key tools UNet uses is something called an indicator function.
An indicator function. Okay, I'm not familiar with that one.
It's kind of a mouthful, but think of it as a mathematical way to enforce rules. It's making sure the output of all those calculations is actually a segmented image and not just a jumbled mess.
Okay, so the indicator function is like the rule book, ensuring everything stays within the lines of what a segmented image should look like. That makes sense. But UNet is dealing with, these are complex images, right? How does it even begin to figure out the right steering instructions for each one?
That's where things get really interesting. You see, UNet, it doesn't rely on pre-programmed instructions. It actually learns those instructions from the data itself. And it does this by using some pretty ingenious mathematical techniques.
All right, you've piqued my curiosity. Hit me with these ingenious techniques. What's going on under the hood of UNet that allows it to, learn and adapt like that?
Well, a core part of UNet's magic lies in what's called multigrid methods. It's kind of, imagine you're trying to solve a giant jigsaw puzzle. Try to do it all at once would be totally overwhelming. Right?
Well, absolutely. You'd be staring at a sea of pieces, no idea where to even begin.
Exactly. So multigrid methods are like breaking that puzzle down into smaller, more manageable chunks. You solve the smaller parts first, and then you use that information to piece together the bigger picture.
So it's a divide and conquer strategy, but for image segmentation.
Precisely. UNet uses this to decompose the image, and more importantly, the control problem itself across different scales. So instead of analyzing the whole image at once, it breaks it down into different levels of detail.
So it's kind of like zooming in and out, looking at the big picture and the fine details, all while trying to steer towards that perfectly segmented image.
That's a great way to put it. And it's all made possible by how these multi-grid methods connect back to that control problem we were talking about, steering the ship.
Right.
You see, by breaking down the problem across those different scales, UNet can actually apply those steering instructions, those mathematical equations, at each level of detail. So it's making, smaller, more precise adjustments as it goes from the big picture down to the really fine points of the image.
So it's not just about analyzing the image at those different scales. It's about applying those steering corrections, those mathematical instructions at each scale to kind of guide that segmentation process, right?
Exactly. sharply. And to do this really efficiently, UNet actually uses something called hybrid splitting methods.
Hybrid splitting. Now, that sounds a little intimidating.
It's actually not as complicated as it sounds. Think of it like this. Imagine you're trying to solve different parts of that jigsaw puzzle, the one we were talking about, simultaneously. You might be focusing on one section, really concentrating on those pieces with your conscious mind. But at the same time, maybe your subconscious is piecing together another part in the background.
So it's like UNet is using different parts of its brain at the same time to tackle those different levels of detail.
Precisely. Hybrid splitting methods allow UNet to combine, sequential and parallel processing. It's like multitasking, but for AI. And it makes it much faster and more efficient at solving that segmentation problem.
Okay, that makes sense. But I'm still trying to wrap my head around how all of this actually connects back to, UNet's actual structure. We've talked about these multi-grid methods, hybrid splitting, the whole control problem analogy, but how does it all come together in the actual, architecture of UNet?
That's where the paper gets really, really fascinating, because it reveals that UNet's structure, the way it's built with its layers and connections, isn't arbitrary at all. It actually maps directly to a very specific mathematical algorithm.
Hold on, so you're saying UNet's entire design, all its complexity, boils down to a specific mathematical formula?
Well, yeah, you could say that. And this isn't just any algorithm. It's one that's specifically designed to solve our image segmentation control problem in a really, really elegant way.
Okay, that's incredible. But how does it work? Can you, break down this algorithm for us a little bit?
Absolutely. Think back to UNet's that encoder-decoder structure.
Yeah, right, with the, the shrinking and expanding pathways.
Exactly. Well, the algorithm actually mirrors that structure step by step. First, it kind of dives down through those decreasing scales we talked about, much like UNet's encoder, and it's simplifying the image representation at each level.
So it's creating a sort of summary of the image at each level of detail, summarizing a book by chapter, then by paragraph, and so on.
That's a fantastic analogy. And then, just like UNet's decoder, the algorithm works its way back up those scales, gradually reconstructing the image, but this time it's incorporating the information it's learned at each level along the way.
Okay, that explains the encoder and decoder parts of UNet. But what about those other crucial components, like the bottleneck and those handy skip connections? What role do they play in this whole mathematical algorithm? So we've got this algorithm, right? It's like mirroring that encoder-decoder structure, simplifying and then reconstructing the image as it goes. But what about the bottleneck and those skip connections? Where do they fit into all of this?
You're asking the right questions. Remember how the bottleneck is where UNet really compresses that image information? It's getting to the essence of what it's seeing.
Right. Getting to the core of it.
Exactly. Well, in the algorithm, that actually corresponds to the stage where it's working with the smallest, the coarsest representation of the image.
So it's like finding the main idea of the image, if we were to stick with that book analogy.
Perfect analogy. It's like finding the main idea of that book. And this is crucial because it forces that algorithm, to really learn the most important features of the image before it even starts trying to reconstruct things.
So it's not getting bogged down in the details too early.
Exactly. It's figuring out the big picture first. And now, for those skip connections, remember those. They help UNet preserve detail as it moves between those different scales.
Yeah, they're like those little bridges that keep everything connected.
Exactly. And the algorithm has a direct parallel to that. It doesn't just, discard information as it goes down in scale. It actually carries forward these key details, just like those skip connections, making sure nothing important gets lost in the process.
So it's almost like it's taking notes, as it's going down the levels, jotting down these crucial details. Then it can refer back to them when it's time to rebuild the image with all the details.
You've got it. That's a great way to think about it. And here's where it gets even cooler. Each step in this algorithm, each calculation it makes, has a direct link to the components we see in an actual neural network. Like UNet. We're talking convolutions, activation functions, all of that.
Wait, hold on. Are you saying those terms that we always hear in AI, like convolutions?
Yeah.
They actually have a mathematical equivalent in this algorithm?
Absolutely. For example, convolutions. Those are the operations that help UNet identify those patterns in the image, right? Well, they have a direct mathematical counterpart in the algorithm. And that determines how information at different scales actually gets combined. And that ReLU activation function, remember we talked about that earlier?
Yeah, vaguely.
Well, that pops up in the algorithm too. And it's basically making sure that all the information that's being processed, you know that it stays within certain bounds. It's like a mathematical safety net.
Wow. So it's not just some, random structure that somebody came up with. It's like every single part of UNet is there for a very specific mathematically sound reason.
Yeah.
It's all connected to this like elegant solution for that control problem of image segmentation.
Exactly. And that's really the main point of this paper. It's arguing that UNet's success, while, we initially observed it through all those experiments and like trial and error, it can actually be beautifully explained as a one-step solution to this, carefully crafted control problem.
One step. So all those layers, all that complexity, it boils down to a single elegant mathematical solution.
Well, to be precise, the paper actually focuses on a slightly simplified version of UNet to illustrate those core principles. It's kind of like, if you want to understand how a plane flies, you might start by studying a model airplane. You don't need all the bells and whistles to grasp the basic aerodynamics.
So they're using the simplified model, but the fundamental math, it still holds true for the more, complex versions of UNet we see in the real world.
Exactly. The core insight remains the same. UNet's power, it stems from this really beautiful synergy between its architecture and this underlying mathematical algorithm. It's not a black box anymore. It's an elegant solution that's rooted in those solid mathematical principles.
So what does this all mean? Like, we've gone from UNet being this, almost magical tool, this black box, to actually seeing the elegant math at its core. What are the implications of understanding it at this level?
I think it's huge. Because if we can understand UNet this deeply, who's to say we can't do the same for other AI systems that seem, mind-bogglingly complex? Imagine a world where we're not just building AI, but we're actually truly understanding the mathematical foundations of how it learns and how it makes decisions.
It's a thrilling thought. And it all circles back to this idea of the control problem, right?
Yeah.
By framing these incredibly complex processes in this mathematical way, by breaking them down, understanding those equations that are really at play, that's how we can unlock those secrets of AI.
Precisely. And who knows what amazing applications and innovations are waiting for us as we continue to explore this fascinating intersection of mathematics and artificial intelligence.
This deep dive into UNet has been, seriously mind-blowing. It's like peeking behind the curtain of this incredibly powerful technology and realizing that, even the most sophisticated AI systems, the ones that are shaping our world in such profound ways, they're built on these elegant mathematical principles. It just goes to show sometimes the greatest mysteries really do have the most beautiful solutions just waiting to be uncovered.